So finally, let's finish this off. What we want to do is find an equivalent Euler-Lagrange equation for a functional with two independent variables, x and y. So we've seen that it boiled down to separating out this value of eta from this equation. So we know that eta of x and y is not equal to 0. So whenever we separate the eta out, whatever's left within the equation here is the term that's going to be equal to 0. In effect, that's going to be our equivalent Euler-Lagrange for two independent variables, x and y. Now we said that we're going to use the Greens Theorem in order to help us separate this eta out for these two terms. And this is the Greens Theorem here. So this is just a statement of what we looked at in the previous video. So let's work through this example here. What we're going to do is we're going to make a substitution for our phi and our psi. So we're going to say that let our phi equal eta partial f by partial p and psi equal eta partial f by partial q. So let's put these substitutions here into this Greens theorem. So the right hand side here is simple enough. We're going to have, instead of the phi, we're going to have the value of eta partial f by partial p. So I've put that in here, eta partial f by partial p, and that's times our dy. And of course our psi here is going to be our eta partial f by partial q. So I've put that in here, eta partial f by partial q, and that's by dx. Now the left hand side here is going to be a partial by partial x over phi. So that's partial by partial x over phi, which is our eta partial f by partial p. And our partial by partial y of psi, well, we're going to have our partial by partial y here, and our psi is going to be our eta partial f by partial q, and that's all by dx dy. Now what we're going to do is we will differentiate out these terms here. So in effect what we've got is a product of two terms, a term in eta and this term here, partial f by partial p. So we'll use the product rule for differentiation. So what we'll do is we'll differentiate this term here and then multiply it by this term, and then we'll differentiate the second term here and multiply it by the first term, eta, and we'll do the same for this here as well. So we're going to end up with four terms. So we'll do the first one just now. We're going to have our partial eta by partial x, and then we'll multiply it by what's left over, partial f by partial p. And then we'll differentiate the second term, so it's going to be partial by partial x over partial f by partial p, and we'll multiply it with what's left over, which is our eta. So we'll get these two terms here. Now we do exactly the same thing with this term here. We differentiate our partial eta by partial y, multiply it by partial f by partial q, we get this term, and then we differentiate partial by partial y over partial f by partial q, and we multiply it by the value over eta. So we've got these four terms here. So let's take this equation here and we can simplify it down quite a lot in the next page. So I've taken a copy of the last equation we've seen on the last page, and that's this here. Now a thing to note is that this function eta of x and y, it's going to be exactly 0 around about its boundary. Now if you think back whenever we did the calculus of variations, we looked at the only one independent variable x, then we would have our value of our function eta of x, and we said that eta of x is defined as 0 at its endpoints. Now it's the same thing for the function eta x and y. So eta x and y is going to be defined as 0, but of course it's not going to be at the end points because it's a function of two variables. It's going to be 0 round the entire edge. So in this case here, this entire edge here actually sits on the xy plane. It's 0 at all points. So it means that if we were to look at the right hand side of this equation here, then we're taking this line integral around the closed loop, gamma. But the eta here, remember, is a function of x and y. So this eta x and y is going to be equal to 0. So this term here will disappear because the eta x and y is equal to 0, and this term here will disappear because the eta x and y is equal to 0. So it means that the entire right hand side of this equation here is equal to 0. So what I've done is I've just rewritten it here. So we've taken this here and we've just simply made it equal to 0. So this equation here is exactly the same as this one. I've just turned that side to a value of 0. So now what we can do is we can then keep this term here on this side, and we can keep this term here as well. And what we'll do is we'll take the other two terms, that is this term here and this term, over to the other side. So we're going to be left with this equation here. And you'll see I've taken out the common factor of the eta for this term and this term. So we've got this equation here on the right hand side. So let's take this here finally, and we'll use it in order to simplify our original equation. So I've just taken a copy of the last equation from the last page. Now what we had was our original equation here, and we want to separate out the value of eta. But now we know that we can rewrite this here in this form here. And you can see here that these two terms here are nothing other than the two terms that we have here. So it means that we can replace these two terms here with these two terms here. And that's what I've done. So you can see we're going to have our original value of our eta times our partial f by partial s. That remains the same. But these two terms here are going to be replaced by the minus partial by partial x over partial f by partial p, and our minus, because it's a minus sign here multiplying everything, partial by partial y over partial f by partial q. And that's all by our dx dy, and that whole thing is equal to 0. And we know that the function eta of x and y doesn't equal 0. So by an extension of the fundamental lemma of the calculus of variations to two independent variables x and y, which we're not going to prove here, we can then say that the thing inside the brackets here must be the thing that is equal to 0 in order to make this integral equal to 0. So finally we can say that our equivalent Euler-Lagrange equation for a functional with two independent variables can be written in the form of partial f by partial s minus partial by partial x over partial f by partial p minus partial by partial y over partial f by partial q, and that's all equal to 0. So this is the equation here that we've been working towards over the last few videos, and that's us really finished with it. Now there's only one other thing that we can do here, is we can extend this to a functional of n independent variables, and we'll simply extend this by taking the partial f by, now let's say we've got a new term here which is a term of multiple independent variables, which is a partial f by partial z minus partial by partial x1 over partial f by partial p1 minus partial by partial x2 of partial f by partial p2, and so on and so forth along to the nth term, which is partial by partial xn partial f by partial pn. So that's how us extend it to a multiple independent variables. But what we're really interested in the final part of this video is this equation here. So this is our Euler-Lagrange equation, our equivalent Euler-Lagrange equation for a functional of two independent variables, x and y. So that's all for this video. Thank you for listening, and goodbye.